completed homework number 5? One student? Okay. So today's going to be our fourth and last lecture that deals with itinerant magnetism. That is electrons that are inside a system, inside a solid. They're free electrons, but they're interacting with one another. Right? So far in this course, when we looked at polyparamagnetism and Landau diamagnetism, electrons not interacting with one another. But now we've introduced interactions between electrons. So we started off with the idea of the Hubbard-Hamiltonian, the tight-binding Hamiltonian. Then we derived a Hamiltonian for the Coulombic interaction between electrons in the quantum field theoretical language, in the second quantization form. Then we employed the Hartree-Fock approximation. And from here we would like to move onward. We've also studied how electrons can lead to paramagnetism. For example, the idea of polyparamagnetism. We've also seen how electrons can lead to diamagnetism through Landau quantization. But we haven't yet seen how free electrons can spontaneously cause ferromagnetism. Spontaneous ferromagnetism means without the application of a magnetic field, you have a sea of electrons and the material is showing ferromagnetism. Okay, so this is what we're going to look at today. So a quick recap, since the previous two lectures were kind of online, a quick recap. First of all, we looked at the Hamiltonian for interacting electrons. And that Hamiltonian we've already derived is given by, it's a ground state, so I call it H naught. It's given by H bar square K square over 2m C K sigma dagger C K sigma. You sum over all the wave vectors K and the two kinds of spins, up spin and down spin. So this is like the kinetic energy part without any interactions. Then we introduce Coulombic interactions, and those Coulombic interactions resulted in an interaction term, factor of 1/2 because we do not want to double count. And then we wrote down, so this is a single particle Hamiltonian. We now write a two particle Hamiltonian. This was our first online lecture. And this Hamiltonian is given by a quartic product of 4 creation and annihilation operators given by CP1 sigma 1, CP2 sigma 2, P1 and P2 are momentums. We're just giving them a different name, a different symbol than K. CP2 minus Q sigma 2 dagger, CP1 plus Q sigma 1 dagger. Right? So these are the sequence of 4 terms. You are annihilating an electron of momentum P1, spin sigma 1. You're annihilating electron of momentum P2, spin sigma 2. And creating an electron of momentum P2 minus Q of the spin sigma 2, creating an electron of momentum P1 plus Q, spin sigma 1, and then all of this must come with some amplitude, and that amplitude is the Fourier transform of the Coulombic interaction calculated at a particular value of the wave vector, which is Q, and then you sum up this is half here. You sum up over both the spin sigma 1 and sigma 2. Each one of them could be plus 1 or minus 1, up or down. Each one of them could be up or down. You then sum up over all the P1s and all the P2s, and you sum up over all the Qs, but you do not include 0, because the Q equals 0 term leads to a divergence, which was kind of annulled by another term which we derived in the first class. That other term was coming out from the interaction between the electrons and the ions in the system. So this is our overall Hamiltonian. This is the Coulombic interaction part, and this is the kinetic energy part. This is kinetic energy, this is potential energy. And if you want to make a kind of diagrammatize this, an electron of momentum P2, spin sigma 2, coming in, an electron of momentum P1, spin sigma 1 coming in, and then there is this electromagnetic interaction, Coulombic interaction, which is resulting in the transfer of a particle of momentum Q. Okay, and this leads to creation of a particle. This electron has kind of decremented its momentum by this Q, but its spin remains unchanged. This electron picks up the momentum Q, and its spin remains unchanged. Okay, so this is the overall Hamiltonian that we have for an interacting system. Now, in the next, and by the way, this VQ, we also derive this VQ. This VQ, this term in the Fourier expansion, is given by E square epsilon naught, the volume of the system, Q square. Okay, this was already derived for you. All right, then we did another approximation. In our next lecture, we invoked an approximation called the Hartree-Fock approximation. Hartree-Fock approximation. In this approximation, we assume we can understand the approximation through this diagram. What we assume is, now this term can contain two kinds of interactions: a direct interaction and an exchange interaction. The direct interaction is, so if you want to compute the energies, we would like to sandwich this Hamiltonian inside the Fermi states. Sure. All the K states filled up till the Fermi level. We saw that the direct interaction was inconsequential because it just meant that an electron was going up out of the Fermi sphere coming down. The other electron was going out of the Fermi sphere and coming down. And no interaction took place. Q was 0, but that term is not allowed. So the only other kind of term that is allowed is the exchange interaction. Now what the exchange interaction means is that if I were to draw the Fermi sphere, this is the Fermi sphere of radius, some radius kf. Okay? With two electrons, they have momentums p1 and p2. Now now one interaction is the exchange interaction, which really means that this electron is picked
up from inside the Fermi sphere, inside or on the Fermi sphere, but inside the Fermi volume, picked up, and its momentum is changed to P2, while its spin remains conserved. And this electron is brought here. So if we compare this with the Feynman diagram, this means that we have a quasi-particle of momentum q, which is simply the difference between P2 and minus P1, which is being exchanged between the two electrons. And the two spins are the same. So sigma 1 is the same as sigma 2 sigma. And this effectively means that we are kind of exchanging the two particles, taking this electron from this point in the Fermi sphere and taking it to that point. Because once this parity operation has been done, overall the quantum state remains unchanged. A Fermi state remains a Fermi state. Therefore, if you sandwich this Hamiltonian from the left and the right by the Fermi states, it gives you 1. It doesn't give you 0. So if you want to have a non-zero energy, the sandwich of this Hamiltonian between the Fermi states must be non-zero. So this is the exchange interaction. So we can codify the exchange interaction in this Coulombic repulsion by having these conditions. So if I just write down the new Hamiltonian, now this is called the Hartree-Fock approximation. If I write the Hamiltonian under these constraints, the Hamiltonian that results is called the Hartree-Fock Hamiltonian. So in this case, H naught, still the ground state, because I'm not, everything remains, the Fermi sphere after this exchange remains the Fermi sphere, the quantum state doesn't change. I can also excite the electron from within the Fermi sphere to outside. I can create an excitation. That will create a magnon. Okay? So you can also have these excitations, but at the moment I'm keeping everything in the Fermi sphere. Okay? So this is still called the ground state, but in the Hartree-Fock approximation, this becomes h bar k square over 2m ck sigma dagger ck sigma sum over k's, sum over the spin variables plus half. Now VQ is V P1 minus P2. This is a term in the Fourier transform. C P1 sigma 1 sigma 1. Let's just call it sigma. The second term is CP2. Now CP2 is P2 becomes P1, correct? So P1 becomes, so if you want to write everything in, so P1, still call this P1. The second term is P1 becomes P2, P2 becomes P1, sigma, P2 minus Q becomes P1, sigma, with a dagger, C, P1 plus Q becomes P2, sigma dagger, right? That's it. So let's call this term H exchange for a minute. Let's just call it H exchange for a minute. Okay? So this is 1/2 sum over P1, P2, and I want to keep both of these, by the way, smaller than KF from radius. Okay? And then I have the sum over sigmas. I do not have sigma 1, sigma 2, I just have sigma. V P1 minus P2 C P2 sigma, right? Inequality तो नहीं कर दी. P2 minus Q is P1, P1 plus Q is P2. The first two terms remain unchanged, so I am annihilating an electron at P1, then I am annihilating an electron at P2, and P2 minus Q now becomes P1, okay? Now this means I have, now if I take this term here, CP2, and move it across this fermionic operator, what's going to happen? I get a minus sign. Okay? So this becomes CP2 sigma. Okay? And then I have CP1 sigma rather CP1 sigma G. इधर नहीं, हम वहां से शुरू कर रहे हैं. CP1 सबसे राइट पे है, फिर CP2 है, तो हमने CP1 को एनालाइज करना है और CP2 को एनालाइज करना है. ठीक है, इनको एनालाइज कर लिया. यहाँ पे इनकी ये वेरिएबल चेंज नहीं हो रहे. ठीक है, फिर हमने जो CP2 माइनस Q क्रिएट हो रहा है वो P1 क्रिएट हो रहा है. ठीक है, so this is our exchange interaction, right? Now this, if you notice, what's this? This is the number of particles of momentum P2, so number operator sigma, spin variable, and this is n P1 sigma. ठीक है. क्योंकि ये उसी वक्त एक्सचेंज हो सकेंगे जब दोनों की स्पिन एक जैसी होंगी. एक्सचेंज का तो ये मतलब है ना, वरना तो वो वेव फंक्शन सिमेट्रिक एंटी सिमेट्रिक नहीं रहेगा. इन दोनों की स्पिन्स एक सी होंगी, मोमेंटम्स डिफरेंट है, तो मोमेंटम वेव फंक्शन एंटी सिमेट्रिक होगा. ठीक है, फर्मियोनिक एक्सचेंज के लिए जरूरी है. Alright, so this is our exchange Hamiltonian under the Hartree-Fock approximation. जी. किसमें? हाँ, क्योंकि Q जो है ना वो P2 माइनस P1 के बराबर है. तो वो अपने P माइनस P2 फर्क नहीं पड़ता क्योंकि इसका स्क्वायर हो रहा है वैसे. स्क्वायर है ना वाला. ठीक है. Alright, so I can write this as minus 1/2. Now, V P2 minus P1 and P2 sigma and P1 sigma. Okay. Over sigma P1. Okay. Now we also kind of found out in the previous class that this Hamiltonian leads to an energy. This term is simply the kinetic energy of all the electrons filled up till the level Kf. So the total energy is dependent on the Fermi energy. And we've already noticed that if we have n electrons in the system, capital N electrons, that the kinetic energy term is 3 over 5 n EF. With EF is the Fermi energy. Okay, this is from our previous lecture. This term, if you find out this, so you take the sigma, the sum over the spins, this will give you, it's a very easy summation, and we've done this in the previous class as well. So this leads to, and I referred to an appendix, a supplementary material in which I asked you to kind of look up the how we integrate. We need to replace this summation over k by integrals, right, of this kind. V over 2 pi cube d cube k, correct? Multiplied with 2 to count for the two spins. So overall the result that we obtained was of this kind. T beta solar. Kf. But this is the Fermi wave vector. So this is the energy of the system of interacting electrons in the absence of a magnetic field, and that's the ground state. This term is simply the kinetic energy of the electrons, and this term is the potential energy of electrons. Okay, any question at this point, G? जरूरी नहीं, नॉन जीरो केल्विन पे चेंज क्या होगा, फर्मी डायरेक्ट डिस्ट्रीब्यूशन, ठीक है? This is for all temperatures. Alright, so now this is our, and then we also simplified this a bit further. Remember we wrote this as 2.2099 RS squared minus 0.916 RS multiplied by the Rydberg energy, 13.6 electron volts. Correct? Where RS is defined as a parameter, scaling parameter with respect to the Bohr radius, which really meant that 4 over 3 pi RS A naught cube. This was given as the inverse of the concentration density of the electrons. This is how RS is defined. Alright? V over N is the inverse of the concentration of electrons. So if you know the density of the material and you know the atomic mass of the material, you can calculate RS. We're going to do this today. So now look at this relationship. Now enters the idea of ferromagnetism. Now there's no magnetic field applied so far. What this exchange term is doing is that this exchange term is lowering the energy. If there were no Coulombic interaction, the energy would be higher. But what the impact of the Coulombic interaction is that it is lowering the overall energy of the system. Okay. Now what we would like to, so this scenario represents all the spins filling up the Fermi sphere up till the Fermi boundary. And those spins are there in pairs. So what's the magnetization of the system? Zero. because as many spin ups as there are spin downs. So this is a totally unmagnetized system. The spins are perfectly paired. They're anti-aligned. So this is unmagnetized. So this energy is really for unaligned spins. Okay? Now suppose we have this scenario. What I'm going to do now is I would like to see, is there an advantage for the spins to align? Advantage means, is there a prospect for lowering of the energy? That's what we want to see. So now we have interacting electrons, system of interacting electrons. Would the electrons like to align themselves? Yes, they would align themselves if the overall energy goes down. Now there are two terms. One is a positive term, the other is a negative term. We really would like to see that, suppose we have a scenario in which there are n plus electrons spin up. Correct? Okay. Now, if n plus equals m, the same n that we're using here, will these electrons go up to the level EF or KF? Or they would kind of fall short or go beyond? एक ही आएगा. So they would like to go beyond. How much beyond? So if I draw a cross section of the Fermi volume, it's a sphere. This is KF for spins. KF is for the anti-aligned spins or paired spins, right? Now if spins, all the n spins are now of one kind, the n plus spins, the Fermi volume is going to expand. It's not going to double, but it's going to expand. Okay, it's going to be bigger. Let's call this KF plus KF up. Okay? How bigger? How much bigger will it be? I give you 4 or 5 minutes to think about this. I would like you to tell me that if all those n spins were of spin up kind, how big will this Fermi sphere be? What is this? What is the ratio of KF plus to KF? Your spin counting is going to replace this sum over k's by an integral. Okay. V over 2 pi cube d cube k, right? So from the 0 point of the k space up till kf, I want to break this volume integral into 3 parts. So what we really have is, so if you take the sum of these, you will get the total number of spin ups. Okay? And you do not multiply this with 2 because you just considering spins of one kind. So V over 2 pi cube. The integral over phi is going to give you 2 pi. The integral over theta is going to give you a factor of 2. So you really get 4 pi here, 4 pi, and then you left with k square, dk, k square, right? Where k is the radius, and this k goes from 0 to kf up. क्योंकि देखो पहले ना जो इलेक्ट्रॉन्स थे ना इस वॉल्यूम तक थे, ठीक है, वो पेयर्स में थे. अब इसमें बहुत से k पॉइंट्स हैं, ठीक है ना, हमें पता है वो उनकी तादाद हमें पता है, जो K पॉइंट से टोटल नंबर ऑफ इलेक्ट्रॉन्स जितने थे ना उससे आधे हैं, क्योंकि हर पॉइंट पे 2 इलेक्ट्रॉन, लेकिन हर K पॉइंट पे इलेक्ट्रॉन्स पेयर में आ रहे हैं, हर K पॉइंट पे, ठीक है, ऑल द वे अप टू द फर्स्ट। अब हम एक सिनेरियो कंसीडर करना चाह रहे हैं इसमें इलेक्ट्रॉन पेयर्ड नहीं है, अलग अलग है। तो अब एक पॉइंट पे 2 पैरेलल इलेक्ट्रॉन्स नहीं आ सकते ना, तो फिर वो पहले ये वाली स्फीयर भरेंगे, लेकिन इससे आगे भी चले जाएंगे, ठीक है, ये बात, इसलिए एक स्फीयर बढ़ोगे। नाउ इफ आई कैलकुलेट दिस इंटीग्रल, I get n plus over the volume is 4 pi 8 pi cube k f cube over 3, ठीक है। So this means kf is 6 pi square n plus over the volume 1 cube, right? Okay. Now, if you were to, I think you've done this several times before. If you were to repeat this calculation for the anti-line case, get a factor of 3 here. That's basically because you have a factor of 2 here. Right, because there are 2 kinds of spins. Okay, so kf is 3 pi square n over v 1 by 3. So really the relationship between kf plus and kf is this thing, 2. Right? So this is how big this Fermi radius becomes, and the corresponding Fermi velocity as well. And likewise, this will also be equal to kf if all the spins were all of them aligned by the way. हम ये नहीं कह रहे कि कुछ aligned है कुछ है, all of them aligned. Whether if they were aligned in the opposite, you will still get the same Fermi radius. Now, what about the energies? What about the E? Will the Fermi energy change if all the spins were aligned? What's the relationship between EF plus and simple EF? ये तो बता दो. So these are the Fermi. And we're just considering the kinetic energy of electrons. ठीक है. So this is 2 by 3. ठीक है, ये मेरे में 1.6 के करीब होता है. So now we have a scenario, if that energy that we've written at the top was really for unaligned spins. We can also suppose that if all the spins were aligned and they were of just one kind, suppose all of them are spin up, then the total energy of the system, so you simply need to replace the appropriate n's and ef's. So you will have, suppose E naught HF for all of them aligned. That's going to be 3 over 5 n plus EF plus, which is EF multiplied by 2. Okay? Minus. So your epsilon pi square epsilon naught n E square kf. Correct? So that's just, if I look at that term over here, the new energy is 2.2099 over rs square into 2. Rydberg. Right? So this is the new energy. When will this energy be lower? When this energy is smaller than that energy. Right? So lowering is preferred, which means ferromagnetism is preferred, and kind of spins would rather like to, they will still like to, they will increase their kinetic energy because dilating or expanding the Fermi volume increases the kinetic energy. They still like to increase the kinetic energy, but that's coming for a benefit because that scenario is decreasing the potential energy because of the negative sign that we have over there. So even though the kinetic energy of the system goes up, because the Fermi volumes are bigger for the aligned case, for the ferromagnetic case, the potential, the drop in potential energy is even larger. So the overall energy goes down, and that happens for certain values, certain threshold of RS. Right? So let's calculate that threshold. So if I were to look at this energy and I want to make it greater than that energy, so I really should have 2.2099 RS squared minus 1 minus 0.916 RS 3 minus 1. I need this to be less than 0. Correct? ओके ऐसे ही है ना, तो मैंने ये एनर्जी ली, उसमें से उसको सब्ट्रैक्ट कर दिया. So I want this to be negative. So in order to find the regime, I want this. So let's look at the critical threshold value. Put this equal to 0. Solve this for RS. Okay. When I solve this for RS, RS has to be greater than 5.45, something like that. Okay. So in real metals, which are these conduction electrons, they have RSs ranging from 2 to 10, 2 to 8, or 2 to 9. Okay. So those metals in which RS is large, the packing density is large, usually means that RS is large, usually means that N is small. The electrons form a dilute system. So for those metals, you can expect ferromagnetism. Now you can also calculate RS. So copper, for example, is non-magnetic. So I can do a calculation for copper, for example. Its density is 8.96 grams per centimeter cube. Its atomic mass is about, I think, 63. So its mass is going to be 63 into 1.67 into 10 to the minus 27 kilogram. So I can calculate the number of atoms per unit volume. Correct? So if I calculate the number of atoms per unit volume, I can find the size of the Wigner side cell, 4/3. So the RS turns out to be, so probably we can give this as a homework, is about 2.2 or something. So most metals, iron, even iron, nickel and cobalt, which are ferromagnetism, they have RS values smaller than this threshold. So their ferromagnetism is not really due to this effect. The ferromagnetism in those metals is not because of conduction electrons, because electrons that are inside bands, inside the d orbitals. So that's different mechanism, slightly different mechanism. But still it gives you a hint of what kind of metals that admit free conduction electrons can become ferromagnetic. Many examples of dilute magnetic semiconductors. which are conductors which are doped with magnetic ions like manganese. They satisfy this property. Materials like europium sulfide, manganese sulfide, etc. They kind of have their magnetism owes to this kind of behavior. So really what we see here is that free electrons, they would like to align themselves if it lowers the overall energy of the system. And this is in the absence of a magnetic field. These are first hints of why some materials can become ferromagnetic. Now we need to do a more proper kind of calculation. Right, and that, any questions? जी. क्यों? ज़्यादा भी हो सकती है, कम भी हो सकती है. All depends on the value of RS. देखो ना, अगर ये एनर्जी है, देखो E aligned must be smaller than E paired. ठीक है? For ferromagnetism. ठीक है ना, अगर ये अलाइन है सारे तो ओवरऑल एनर्जी कम हो रही है, तो यू कैन एक्सपेक्ट टू सी फेरोमैग्नेटिज्म. ठीक है. नजर नहीं आए, लेकिन इन मटेरियल्स में नजर आएगी. गैलियम मैग्नेटिक सेमीकंडक्टर्स में, इन मटेरियल्स में, बिस्मुथ में, ठीक है, उनमें नजर आएगी. So the course will end on why iron, nickel and cobalt are ferromagnetic. That's where we will end the course. Okay. Now what we would like to kind of see is, I would like to recall something that you've already learned. That's about polyparamagnetism. So you have electrons. So have you tried any magnetic field here so far? No. So everything is spontaneous. It's a lowering of energy, the interaction between the electron, the Coulombic. We quantized the Hamiltonian, the second quantization form, and from there we went on and found out the energies and see under what conditions is the energy minimized. Now I just want to do a quick recap of polyparamagnetism, because next what I'm going to do is probably in the next series is a Stoner model for ferromagnetism, which is a more complete model, right, which can also correlate with bands as well. So, but before that, I would just like to do a brief recourse on polyparamagnetism. We've already seen polymagnetism, paramagnetism. The Stoner model is derived in principle from, is motivated by polymagnetism. So, we want to move on to the Stoner model of ferromagnetism. So, by the way, this kind of treatment is kind of, I could not find a single textbook that has all this treatment in the condensed form and in a form that is at the right level for this course. So, polyparamagnetism, as you all know, has spin split bands. So, if I make a plot of the density of states, this is my energy. Then I get in the absence of a magnetic field, I get these two bands, right? One is spin ups, the other spin down. No? So, iski jo, this is half of the density lies here and half of the density lies here. Both of them are the same for me. Now I impose a magnetic field. So paramagnetism only manifests in the presence of an external magnetic field. So what happens in the presence of a magnetic field? Zeeman interaction kicks in. Spins that are parallel can lower their energies. Spins the other. So this kind of band which is contagious for the two spins. It splits up. And one of this band is lowered, the other band is raised, right? This lowering is minus mu VB, and this raise is plus mu VB, where mu B is the Bohr magneton. Okay? Times the number of electrons as well. Initially. Okay? So, but we can consider what's happened per electron. Anyway, so now this is the inequilibrium condition. The two Fermi levels inside the material cannot be different for the two bands, the two spin kinds. So some electrons flow down from this level to this level. The chemical potentials, if you look at statistical chemical, the chemical potentials become different and they would like to equalize. This is the process of spin scattering takes place. So if an electron would come from this band to this band, it must reverse its spin. Okay? This is what happens even in electronic systems when you make a p and an n junction. You have a difference of Fermi levels in the p type and the n type. And then this difference disappears and a junction is formed. Okay? So this is beautiful physics. This is really, really nice ideas that are at work in magnetic systems and electronic systems. Now when equilibrium is finally re-established, more spins of one kind will appear. So overall the band structure is going to then look like this. Okay. So this is our EF. EF is the same for both the spin split bands. Now we would like to find out, so per unit volume, n alpha, so let's call the spin alpha, let's call the spin beta, and alpha minus n beta. If you want magnetization, you multiply this with mu VB. This will give you the magnetization. The system becomes magnetized. And you remove the magnetic field, the energies will equilibrate once again, the reverse thing happens, and then get to original. Now, how do you calculate this Na minus Nb? कैसे calculate करेंगे? कैसे किया था हमने पहले? You do a spin density, you do an integral over density. So n alpha, for example, is going to be dE, integral of dE, integral of energy. You need the density of state, which is 1/2 G3dE. Okay. Okay. You need the Fermi-Dirac distribution function. That's it, right? And your energy is in fact E has to be replaced. E plus UdP, right? And this integral now is from minus UdP to EF. Correct? And n beta likewise is going to be given by 1/2 dE UdP to infinity, or EF, first stage EF, half G, the density of states E minus UdP. Right, so this is how you calculate the number of मेरा नहीं ख्याल, क्योंकि ये जीरो लेवल था ना, इस पे ये बैकवर्ड शिफ्ट हो गया। अगर ये हो वो पीछे चला जाए तो मेरा प्लस साइन आता है मेरे ख्याल, क्योंकि नाउ जीरो पे वैल्यू वो है जो आगे थी पहले। So then you subtract the two. So at 0 kelvins, this is 1 for energies less than EF. Okay. So you can replace, so if you're at 0 kelvins, this becomes 1 for energies less than EF, and you can integrate up to infinity. Okay? And these mu v, these are really small values, so you can replace these by 0. And then you do Taylor series expansion. Finally, you get really, you get what it is, you get demagnetization. So the calculation worked as follows. So M is mu b 0 infinity dE of G E BB minus G E minus BB. Correct? अभी फिलहाल हम लिख भी सकते हैं फी, ओके। वो इसलिए लिखा है क्योंकि बियॉन्ड EF this value is 0, right? So this is replaced by 2 mu b partial E computed at E, correct? So now you have this term multiplied with F. You can do an integration by parts, and finally you will arrive at some magnetization, and then you replace B by mu naught H, and you get the susceptibility, which is plus 3 over 2 n number density mu naught mu b square over kb Tf. Tf is the Fermi temperature. Okay. We also know that kBTF is in fact the Fermi energy. Is in the denominator we have the Fermi energy, and mu naught mu b square. kBTF is the Fermi energy, correct? EF. We also know that, by the way, one thing to remember is that the density of states at EF is 3 over 2 n over EF. So the Fermi energy and the density of states at the Fermi energy are inversely related. Okay? So this is in fact proportional to the density of states at the Fermi energy. So the density of states at the Fermi energy really kind of determines what the magnetization of the system is. All the action is happening at the Fermi energy for these electronic, for these Pauli systems. These are all Pauli systems. They obey the Pauli system principle. They're all fermions. Right? So if you have a neutron star or a white dwarf. It's exactly the same physics over there as well. Now the question is, so if you look at this system, these two kinds of spins, they are changing their energies with respect to, because of an applied magnetic field. Now for a Stoner model, which is a model for ferromagnetism, this same kind of splitting occurs in the bands. But that delta over here, the delta that we have, so this is delta. This delta does not really come from an applied magnetic field. It comes from some spin polarization that already exists in the system. You see, I can define a parameter, gamma. Okay, let's talk about Stoner. Let's begin talking about the Stoner model. Now, the Stoner model tells you why a material can be spontaneously ferromagnetic. Spontaneous paramagnetism is in fact ferromagnetism, spontaneously, without the application of a magnetic field. And this is a large effect. We now show that how the exchange interaction kind of contributes to this. The energies that we've calculated and the Hamiltonian, the Hartree-Fock approximation, how that contributes. So suppose we define a parameter psi that is n plus the number of up spins minus n minus over n. You just kind of normalize. So the n electrons are divided into two sectors. Some fraction have spin n plus, some fraction have spin n minus. Some of them have spin. If both are equal, then this factor is 0. If all the spins are spin up, then this becomes equal to 1. If all the spins are spin down, this factor is minus 1. So this is a factor that ranges from minus 1 to plus 1. This is the purely non-magnetic state. And then you have some spontaneous ferromagnetism here, some spontaneous ferromagnetism here. If these zetas are allowed. At the extremes, you have perfect alignment. The kind of thing that we studied over there, perfect alignment. Here you will also have perfect alignment. In between, you have something different. If you had this configuration, all the spins are spin up, then the Fermi sphere is bigger by 2 raised to 1 by 3. The Fermi energy is bigger than 2 by 3. Now what if you have a zeta that is neither 0 nor 1 but somewhere in between? Then some of the spins will have their paired counterparts, others, extra spins, will give rise to some spin polarization, some magnetism, some magnetization. Okay, so you're gonna veer into this direction, you go here, it is तो आपके पास मैग्नेटाइजेशन बढ़ रही है और स्पॉन्टेनियसली बढ़ रही है किसी वजह से. तो फिर फर्मी एनर्जी का जो स्फीयर है ना, ये वाला ये दरमियान में होगा. So this is the scenario for zeta plus 1 or minus 1. और दरमियान में कुछ और होगा. This is the scenario for zeta equals 0. In between you have something else. So if you notice that my n plus is n by 2, 1 plus zeta, right? I'm just kind of rearranging this. My n minus is n over 2, 1 minus zeta, okay? Zeta is a kind of spin polarization parameter, it's a parameter. So instead of writing n plus n minus, I can write n, I can specify the spin system in terms of n and zeta. Okay. Now, the Fermi energy, can you kind of tell me what the Fermi energy would be for n electrons spin polarization zeta compared to the Fermi energy for n electrons and no spin polarization? So when zeta is 1, this is 2 raised to 2 by 3. In the general case, ये क्या होगा? क्या फैक्टर आएगा? Maybe ये आएगा 1 plus, ठीक है ना, एक वो प्रॉब्लम होगा. So when zeta is 0, unpolarized system, right? So you just have the Fermi energy. Zeta is 1, fully polarized. You have 2 raised to 2 by 3. In between you have something else, right? So you have, do this as a homework problem. You have these spins with a particular spin polarization. कुछ उसमें से पेयर अप हो जाएंगी. वो कितनी होगी? जो मिनिमम है उन दोनों में से. पेयर बाकी जो हैं वो अनपेयर्ड होंगी, दो पोलराइजेशन कॉज करेगी. That will be the net spin polarization of the system. उस हिसाब से the Fermi energy will become bigger or smaller. Now what you need to do, you need to, this tonal model that we'll do next Tuesday kind of takes this Hamiltonian over here. जी.
वहाँ पर zeta का modulus क्यों होना चाहिए 1 plus zeta? Because like where zeta is -1, where we can do.
ठीक है. ठीक. Now what you would like to, the Stoner model has one or two approximations. It's a further approximation to the Hartree-Fock model. The first approximation is that this term here, now this depends upon Q, it depends upon P2 minus P1. This term here is really E square epsilon naught V P1 minus P2 modulus square. ठीक है? Now it depends upon P1 and P2, so it's inside the summation sign. Now if you have this large system, what you could do is you could kind of do an approximation in which this P1 minus P2 is replaced by a constant wave vector. Okay? Some Q. Actually, this is another model in condensed matter physics which is called the Thomson-Fermi screening. And that model replaces this K-dependent, this wave vector dependent Fourier transform into constant. Okay? So remember that, and this kind of screening is very commonplace in atomic physics. So you have an electron in the outer shell of an electron. So what atomic number, how many protons does it see? If the atomic number is Z, it does not see all the Z because it is being shielded by intervening electrons. So the atomic number for that lone electron in the valence shell is not Z, it's Z minus some shielding parameter. Okay, so that kind of shielding also takes place, screening also takes place. The net effect is, and I don't want to go into the details and it's a kind of different topic, this is replaced by a number which is independent of the wave vectors. Okay, call it E square epsilon naught V Q Thomson-Fermi wave vector, which is independent of all the Q's, P's and P. Right? So you take this out. So you call this a sum energy. So this has dimensions of energy, of course, right? So all of this is energy. So this comes out of the integral. And then you have a sum over two number densities. But then you also need to make another change. This kinetic energy is now changed. Just as in the polyparamagnetism model, it has an additional factor which comes out. So there are two kinds of spins, spin up. So the spin up electrons, if there is a spin up electron is being impacted by what magnetization it sees. That magnetization depends upon the spin polarization. You see, when a spin up electron, where is this? I'm giving you a physical picture. Where is this splitting coming from? This lowering of energy is really coming from an electron in this spin band, spin up, is seeing a magnetic field. Okay? That magnetic field is extraneous to the sample. It's exogenous. It does not exist inside the sample, it has been applied from outside. Now what if this electron sees a polarization of spins, polarized spins? So the surrounding the spin are other spins, and there is a preponderance of spins of one kind over the other. यानी आसान उर्दू में ये कि भी एक स्पिन है, वो बहुत सी स्पिन को देख रहे हैं लेकिन उसको स्पिन अब ज़्यादा नजर आ रही है. क्यों? क्योंकि ज़ाय नॉन जीरो है, ठीक है? क्योंकि उसको एक स्पिन पोलराइजेशन नजर आ रही है. उस स्पिन पोलराइजेशन वो अपनी मैग्नेटिक फील्ड प्रोड्यूस करेगा ना इफेक्टिवली, ठीक है? एक मैग्नेट अपनी मैग्नेटिक फील्ड प्रोड्यूस करेगा, तो उसकी अपनी एक मैग्नेटिक फील्ड होगी जो बी का काम दे रही है. एक एक्सचेंज इंटरेक्शन की वजह से एक फील्ड है, उसको एक्सचेंज फील्ड भी कहते हैं. इफेक्टिवली उनको एक फील्ड देख रहे हैं. इस तरह की थ्योरी को कहते हैं मेन फील्ड थ्योरी, कि बाकी जितने भी स्पिन्स है ना वो मैग्नेटाइज्ड हैं. उस मैग्नेटाइजेशन की वजह से एक मैग्नेटिक फील्ड देख रहा है ये वाला स्पिन, तो इसकी एनर्जी लोअर हो जाएगी और इसकी एनर्जी बढ़ जाएगी, क्योंकि ये दूसरी तरह की स्पिन्स ऑपोजिट डायरेक्शन में देख रहे हैं. चुनाचे because of this internal magnetic field which arises out of the spin polarization, you see a lowering or increase of energy. So this kinetic energy term also changes. So instead of minus mu v b, you will have terms of this kind: h bar square k square over 2m minus some energy u, some energy term, and a spin polarization psi m. ठीक है? इस तरह की term, यानी this is an effective magnetic field. This thing is an effective magnetic field, and this is some energy term. So I'll explain this. The other kind of spin will see this same term with an opposite sign. So exactly the same impact happens here. Now the kind of calculation for the standard model I postpone till Tuesday. ठीक है? So this is the basic idea. Spontaneous ferromagnetism can occur because of some net polarization that already exists in the system. So how do you solve an example of this kind? You see, if there is some net polarization, is there an advantage in the energy? ठीक है? ये इस तरीके से ही काम होता है. जी
सर, ये एटॉमिक नंबर पे भी डिपेंड करेगी.
क्या चीज़?
ये जो पोलराइजेशन की स्ट्रेंथ है, मतलब वो जो स्पिन का चेंज मेन फील्ड.
अभी हम नहीं, अभी हम सिर्फ कंडक्शन इलेक्ट्रॉन्स देख रहे हैं.
नहीं, मतलब मैं ये कह रहा हूँ कि
ये चीज एटॉमिक नंबर पे डिपेंड करेगी. ये थॉमसन फर्मी, ये चीज, ये आयंस के एटॉमिक नंबर पे डिपेंड करेगी.
इस पर्टिकुलर केस के अंदर जिस तरह हम बात कर रहे हैं कि लेट्स से एक उसकी स्पिन डाउन है,
नहीं,
वो डिपेंड नहीं करेगी कितनी.
वो तो देखे ना, उस पर डिपेंड करेगी जब हम एक और हैमिल्टोनियन लेके आएंगे जिसको स्पिन ऑर्बिट इंटरेक्शन कहते हैं. वो डिपेंड करता है जी की फोर्थ पावर पे. ठीक है? तो अभी यहाँ स्पिन ऑर्बिट इंटरेक्शन की कोई कंसीडरेशन नहीं है. ठीक है? चलिए, अच्छा ट्यूसडे को मिलते हैं आपको.